Well, hello, everyone. Welcome to the Sandbox Summer webinar series. So today, what we're going to be discussing is how we move beyond containers in, the cloud native ecosystem. I think that we've seen a couple of recent incidents that we're going to discuss that will elicit some of that conversation, and how we can kind of focus toward moving toward a future where we have greater isolation guarantees by using microVMs and talking about why those are essential for multi-tenant or even untrusted code. I'm Jed Salazar. I'm the head of security here at Edera, and I'm joined by Alex Zenla, our CTO.
Hello, good to be here.
All right, so if you have any questions, please feel free to put those into the chat in real time. We are more than happy to, keep this an open and engaged conversation. Otherwise, Alex and I are just going to be here, sharing our thoughts. And Alex has a great presentation to cover as well. All right.
Also,
So, before we get into the meat of the webinar, of course, we have to talk about the elephant in the room, which is yesterday's news. So, for those of you who are unfamiliar, um, I think maybe a week ago or so, Hugging Face had released some, kind of a notification to their customers that there had been a compromise to their production environment, and they indicated that this attack was carried out by AI. But at the time, they didn't really know who was responsible for that. And of course, yesterday, as kind of a follow-up in response to that, OpenAI released a kind of a detailed breakdown indicating that it was actually one of their GPT models. I think it's Sol 5.6, as well as an unreleased model used in combination that was responsible for compromising Hugging Face's production environment. And what was really interesting about that is that there was no human at the wheel here. This was a fully automated, attack and successful compromise. And what makes it even more interesting, which we'll probably get into, is that this was based on an evaluation, a kind of widely known evaluation called Exploit Gym, where this seems to be a pretty kind of quintessential alignment problem, where basically this unpublished model's task was to go through this evaluation and see what its score was going to be, and it thought that the best way to achieve that was to basically take the sandbox that it was living in hostage and break out of it and traverse all the way towards Hugging Face's production environment, which is where that evaluation was being stored, so that it could essentially do the best in the model, right? So we had some input saying do the best that you can in the model or on the evaluation, and that's exactly what it did with some very unintended consequences. So that's a little bit about kind of what happened. Alex, what do you think about all of this?
well, I've been waiting for this day, to put it mildly, for kind of an inflection point of the way that we've been building things, combined with the non-determinism of AI. Um, I think it's a really interesting exploit because you have two people involved, both of which had problems, both in architecture, but also in, I think, the natural state of the world that we're in, where AI is just completely surpassing human capability in a lot of cases. Uh, and I think probably one of the more interesting things to start with here is like how the vulnerability came to be, and basically how it pivoted, because that was kind of the root of the problem. My understanding from reading is that it basically used a package cache and poisoned a package cache, which is incredibly interesting. As soon as I saw that, I immediately went, "This is a consequence of how we've been building software, and arguably wouldn't have happened in like an immutable system." Dare I say that Nix might have solved this particular thing, because you could reproduce an entire image outside and then execute it inside of an immutable area, but instead of contacting the network. So the fact that it was able to get network access, I think, is fascinating. And then you just talk about the Hugging Face side of things pivoting and to the host. is obviously what we are very focused on trying to solve. And I think uh, it's it's a combination of shocking and not shocking for me. I would like to think that the vast majority of people in the AI space recognize the problem and are building against that problem, but I think that too often we are too comfortable with the tools we know, and instead of architecting for the future, we're kind of stuck with what works.
Yeah.
What's your thoughts on that?
Yeah, I absolutely agree. I mean, I think going back a little bit, what I find interesting is that, the fact that this agent was placed in a sandbox. And for those of you who are kind of unfamiliar, you know, basically the industry is kind of like under a wide consensus that like because these systems are non-deterministic, because they actually have so many unbounded capabilities, like the ability to like install packages, make outbound network connections, etc., that we should run these systems inside of a sandbox. I think that kind of differs from standard untrusted code, where if you're executing, like, for example, stuff from the open source that you can't vouch for, or maybe even known vulnerable software, that there's still kind of a lack of people's kind of adoption to running things in a sandbox or isolating them properly. But this component was specifically in a sandbox and isolated. The sandbox is kind of a broad term, and what it referred to here is that it did not have egress internet connection, so it could not talk to the outside world. So it found a way to break out of its sandbox and basically achieve its objective of kind of breaking out of the OpenAI, sorry, the OpenAI's environment. What's interesting to me is that this kind of defeated the sandbox that the OpenAI team had placed on it. Like, I know that the OpenAI team was aware that they had the cyber protections disabled for this given model, so they kind of assumed that this was something that is untrustworthy. And despite all of that, it just kind of showcases that it's really difficult to get sandboxing right. Isolation is not as trivial as people think. It's not just a binary thing. I know here at Edera, we think about that really often, and there's a huge degree of isolation anywhere from like container namespaces all the way to kind of what we live at, which is very strict hardware isolated security boundaries. So I'm just curious, like, what do you think about breaking out of sandboxes? Like, is that an interesting thing, or is it really just that the industry hasn't even adopted sandboxes, so we're not even there yet?
I think in this case there were some hopeful things where people did, I think, recognize the need for a sandbox, but I think what's important to understand is sandboxes are kind of like a warm blanket for a lot of people, but people don't really understand, I think, how deep these problems can go. Because while you, as a developer, are seeing, a small portion of the problem, AI can see infinitely many versions of the problem and infinite depth, right? That's why things like side channels and CPUs are scary. That's why kernel vulnerabilities are scary. That's why basically every level of memory unsafe code in the system is scary to me. And honestly, like Unix in general is a little bit scary to me from a blast radius perspective. And so I do think that we've leaned too much as a kind of industry on this idea that like this is a thing that you just do. Like you do it and then it's done. When the reality is like how you configure it matters. What your threat model is matters. I mean, I think fairly often I give a very funny talk on this point, but we as software developers tend to not really think too much about hardware, and the hardware people seem to not really care much about the software developers. And so we have this layer where people there's like a direct separation between the layers of the system, but only when those two things are run in unison can we have a truly secure system. You need only look at the Apple ecosystem a little bit to see that that integration of software and hardware has been a major benefit for their security and what they've been able to do. we have to take that point more seriously. And, what I really tried to do with Edera is I was a hardware person in a sense that I loved hardware and IoT and all of that, but I also loved the software side of things. And marrying those two things together in a way that was meaningful mattered to me. uh, the average person uses Kubernetes for their deployment model, and Kubernetes' whole philosophy is basically ignoring the hardware and creating an abstraction layer to schedule across different hardware. And I think that's just not a world that we could live in anymore.
Yeah, I completely agree. And what's interesting to me about this specific incident is that, you could chalk this up to, okay, well, OpenAI needs to, think, maybe more granularly about how they can start to contain some of these more sophisticated agents. But the reality is that this wasn't a typical exploit. If you think about from an AI perspective, what AI has been good at doing so far is kind of like, vulnerability discovery, maybe even exploiting a given vulnerability. But what happened here is that it basically chained together several highly sophisticated mechanisms where it identified a vulnerability, it exploited that, and then it kept on going. And then basically like looked more like a long tail operation that you would see coming out of a nation state than you would see just out of a standard, Claude model or OpenAI, GPT that does one single task and does it pretty well. And I'm thinking that that is really a wake up call to the entire industry. So Hugging Face had no relation to this model's objective, but they became very relevant from the perspective of, they ended up being attacked and their environment ended up being compromised. So from my perspective, it's like who, even if you have a threat model, if that threat model, creeps out into the wider world with the alignment problem and non-determinism, how are people going to start defending against these, advanced capabilities?
Well, I think it's a hard problem. I mean, I think we would like to aspirationally believe that all risk will be mitigated, right? But the reality is that there is always acceptable risk in every scenario. Um, I think that the window of acceptable risk has to close a little bit. We have to do better on what we think is acceptable because of the types of things we're seeing. I mean, nation state level attacks from models. I mean, this attack is pretty advanced, and some of the stuff you see with Mythos is pretty advanced as well. And I strongly believe that um, everyone should be thinking in those terms. Now, is it comfortable or exciting to think like, oh, everything can go wrong? Well, to me, kind of yes, but I think it is largely uncomfortable for people. And something I'll touch on in my presentation today is actually about that software engineers and particularly systems engineers, we're talking kernel developers, etc., need to do better on making things easier and more approachable for users so that they don't feel like they have to like get a PhD to understand how, the kernel security mechanisms work, right? Um, and I think that is a critical part of how we do systems design. And I think it goes to show in this day and age with the non-determinism, we really can't afford to not do this. Like the same Linux that we were using to mess around with in the I don't know, 2005 maybe, when things were slightly less security focused, let's say, is the same Linux of today. Now, has it gained a lot of features? Yes. Has it gained a lot of security features? Absolutely. But they're very piecemeal. They're not, a cohesive strategy. And I also don't think the answer is, by the way, build a second system, not the least of which is second system syndrome. Basically, every new operating system after Linux has tried to do too much. Um, and so I don't think that's the answer either.
Yeah, I think we're still in the world of like, the multics concentric ring security boundaries, where you're either
Yes.
root and you are all powerful or you're nothing. And that translates directly into the world of containers. That's one of the things that I know Edera is working on directly is having something that looks much more like, a lack of ambient authority, a very small trusted compute base, and a completely isolated environment away from what that authority looks like, whether that's, shared file system resources or whatever the case might be. I think that that's the world that we need to move toward when you have anyone, who now has nation state level capabilities. I think that in the past it was less relevant to worry about, someone finding a kernel vulnerability to do a container escape, because that required a very sophisticated set of skills. However, now it's just an API call. And if you have access to, one of these models that's, capable of finding those for you, or, running an open model that has all of its cyber protections ripped out, then defenders really need better tooling. And, isolation really needs to be, I hate to say this term, but a first-class citizen, highly prioritized, whatever you want to call it. It really is no
Yeah.
longer optional.
Yeah, and I think it doesn't have to be scary or unapproachable either. I think we have done a good job of internally of trying to really think about how do we make adoption easy enough of these technologies that people aren't re-architecting. And I think that's a critical point of uh, all of this is we can't ask people to rebuild what they have. That's not realistic. Even though, the hype is like, oh, AI can rewrite everything. And to be fair, in some cases, there are things you can do with AI, very powerful things like rewrite it in Rust is a thing that's become popular. You might see that Bun, the JavaScript runtime tool, is did a rewrite in Rust using completely AI. And I think those are the things that like sound really cool and hot to software developers, but there's a lot more than that, I think, that needs to be done. And we can't really afford to um, make the developers pay the cost in order to adopt it. And that's really what Adara is focused on is it's that security, being able to ratchet up your security as well. Like you don't have to go all in on like, assuming everything can possibly go wrong and then making it hard on your developers, right? You can ratchet that up over time. And I think that's a critical design of Adara that sets us apart.
Definitely. And I know that this is one of those topics that has kind of captivated the, interest of the public. So if anyone in, on the call has thoughts or hot takes or anything like that, definitely drop them into the chat. Um, but yeah, otherwise, I think it's maybe
Yeah.
time for the presentation.
Yeah, let's go for it. I
Awesome.
think it'll be a good lead in, and then we'll take questions at the end as well on both topics. So I think it'll be great. So yeah, let's do it. So fundamentally, one of the things that I am really curious about in the industry is what do people really mean by container isolation? Um, and containers don't really contain, and it's been a thing that we say a lot, but what does that mean? So I think that's a really important thing for us to talk about first. Um, a container is not a security boundary by default. I touched on a little bit of this already, I guess, in some of my discussion on the new report out, but I think we have the two things in Linux that are built as primitives, which are actually designed as containers. So if you think about Docker, Docker is composed of namespaces and cgroups combined. And namespaces isolate what a process sees. So you can think of that as like a PID namespace, a network namespace, a mount namespace, user namespace, IPC, UTS. And I think, probably someone will come up with another one in the next few years and it'll be confusing. But on top of that, you have C groups. I would say probably most users probably know what a C group is, and that's I talk to a lot of people who actually, when I talk about containers, they tell me that it's a C group, because I think the C and C groups feels like containers, but it actually means control groups. And I think that's really interesting because C groups actually provide no security on their own. All they do is isolate what the process can consume resource wise. So I think that's really interesting because C groups on their own can maybe eliminate overuse and kill a process if they try to consume too much memory. But on its own, you can still see system resources. And ultimately, Linux and Unix in general is very multi-process. So even if a C group can only access a certain amount of memory, it can probably influence the rest of the system in order to consume other resources. My example that I like to give all the time is if you use Btrfs, and this actually bit me in production, which is why I use it all the time. If you use compression in Btrfs, the CPU that is used to do the compression is not accounted to the process that wrote the file. It's accounted to the root kernel task that handles Btrfs compression because that's a kernel task. It's a separate process. So C groups don't actually provide the full resource isolation that you may think. Now they do account for some kernel aspects, like if you make a system call, the system calls like internals inside of Linux are accounted towards the C group. But if you have secondary effects in the Linux kernel, those are not accounted. Namespaces are an attempt to effectively limit the resources within the kernel that can be seen, or potentially, honestly, namespaces are often used more for providing convenience to developers. Like if you have a separate mount namespace, for example, you can do a whole bunch of interesting things. Same with networking. You can do all those things. And then on top of that, they can provide some level of security in the system. But you really have to enable all of the namespaces. And then, interestingly, things like user namespaces are kind of a very confusing thing because they do create separate users and they do allow you to do things like map UID 0 within a container into a different UID and all of that. But interestingly, they also allow you to execute more bits of the kernel. Even though they may be denied, that gives you more attack surface in the kernel. So in some cases, user namespaces can actually increase attack surface. But more importantly than anything, all of this runs in the same shared kernel. Linux on its own effectively runs in one single address space for the purposes of this talk, at least. It runs in one single namespace. It gets more complicated than that, but the reality is that the root kernel can access everything in the system. And really, a container is a UX abstraction. The kernel doesn't really know anything about a container. A container is sort of a collection of features in the Linux kernel combined in order to create some sort of concept that you know and maybe like or love. So I already touched on a little bit of this already, but namespaces aren't isolation. So namespaces will give each container its own view of system resources, resources that may be consumed or potentially like isolating of the resources themselves, but not a full system isolation. So PID1 is inside of a PID namespace, and an isolated host name is what really this amounts to. Like if you're just executing a shell, that's what you'll notice immediately is PID and UTS, which is the host name. And then they also have private mounting and network stacks. They're very cheap because the cheapness comes from the fact that it's effectively just setting a few parameters in the Linux kernel. Importantly, processes inside of a namespace are the same thing as a process outside of a namespace, just with a few namespace tags alongside of it, so that the resources it can see are different. There's no hypervisor involved. There's no interesting magic. There's no advanced technology, really. It's just providing a view of resources. So what that means is that they don't isolate the kernel at all, effectively. The kernel is still one shared address space. If you get root and you have full permissions inside a privileged container, you can own the entire system. Uh, and you can't prevent kernel exploits with this. Any attack surface, any system call that you can successfully make, or even if you can execute or influence any sort of access controls in the system, you are effectively opening up more attack surface. And we've seen time and time again, as we'll see later in the presentation, that kernel vulnerabilities do exist. And as we talked about earlier as well, these kinds of things are going to become more and more common with AI, and we're seeing we don't have all the details yet on exactly what happened there, but I can guarantee it's some sort of sandbox escape at the very least. And your kernel is also not just the kernel itself; it's the entire user space that's driving that kernel. Importantly, Linux is not really self-contained. The kernel itself doesn't do a whole lot. And you can't defend against system call abuse, so um, you you can limit system calls, you can do things like seccomp, but ultimately, if a system call gets entered into the Linux kernel and there's a vulnerability there, there's a huge chance that you can activate vulnerabilities. Also, another thing that's not very well understood is by I think the broader community is that the Linux kernel is a constant moving target. I don't know exactly when the last system call was added, but it does change over time. There is some stability guarantees in the Linux kernel as it relates to user space. Um, but the system calls do change and do gain new flags and new features. So a system call that's secure today may not be secure tomorrow. And of course, the kernel developers do care about this, but that doesn't mean they make mistakes. Sometimes a human element is a component of a kernel exploit. And then probably one of the most important things that I think about a lot is side channel leaks and other vulnerabilities like that. I mean, the kernel basically doesn't provide any side channel leak prevention by default in any sort of container stuff, aside from what's already in the kernel. You do have Spectrum Meltdown, all of that, but there's other types of side channels that aren't CP vulnerabilities. So we're talking other daemons, stuff like that. Um, I already touched on this a little bit, but C groups are accounting, not policing or policing. And C groups limit resources. They don't prevent abuse of the kernel. So a tenant can still make system calls against the shared kernel. So think about this, right? Every system call that you can make is effectively a, a way to enter the kernel. You've called use a kernel space. Um, a lot of people probably don't know this, but when you call kernel space, it quite literally switches into a privileged mode. It's how the kernel is able to execute stuff, right? The CPU knows that you've called kernel space. It swaps to a privileged mode and then goes back when you return back into user space. Of course, I'm oversimplifying a little bit, but every time you're doing that, you're going into a privileged space. So keep that in mind in your in the way that you think about security. You can still trigger kernel bugs and you can affect scheduling and cache behavior. C groups are not C groups can get off some of the way there on helping with noisy neighbors because you can limit resources, but it's not granular enough, and especially the way people actually use it versus what they're capable of. It's not granular enough to truly prevent noisy neighbors. If, for example, if you have, let's say, you somehow are using a one CPU core system, which hopefully you are not, but obviously, things are going to contend on that single core, and cache behavior is heavily influenced by what's running. The kernel gives you time slices and stuff like that. If it has to schedule across multiple processes, there's a chance that performance will not be consistent. Um, and this is one of my favorite lines in the whole thing, but multi-tenancy via namespaces and C groups is multi-tenancy by politeness. Effectively, you're just giving some sort of constraints. And you can see this in the container ecosystem a lot. It just feels like a constant, like plugging the hole type of situation. I really encourage people to go look at how a runc container config actually looks. It's literally doing things like mounting over dev files and stuff like that to create some semblance of isolation that's not really there. Uh, so what does this really mean from a practical perspective if you have a multi-tenant workload? Uh, if you have a whole bunch of tenants, if they are only using namespaces and C groups, they are still sharing one single Linux kernel. The Linux kernel is massive. Now, of course, the Linux kernel that you may be actively deploying is, I don't know, 10, 20 million lines of code. The full kernel space is 40 million or more, and over 450 system calls, or about 450 system calls. And I think that's really important to understand that, like, there's a lot of things you probably don't know about in the Linux kernel. There's also a lot of kernel modules that are particularly scary. And if you're running privilege mode, you can do things like literally inject code into the kernel. So there's possibilities that you may not even consider that can completely break the multi-tenant isolation if you're using namespace and C groups on their own. So one single kernel bug or misconfiguration, or even just something you didn't know could happen in Linux, is every tenant is compromised on the entire node. That's why clouds often, the ones that actually care about security, are not doing containers because rather they're not doing containers on a single shared host. They're giving you a virtual machine running those containers because they have a responsibility to secure you. And so they know that this model does not work for the security of the system. Let's talk about some CVEs. I'm not going to go through all of these, but there's a ton of things that exist. There's a ton of them that have already happened since this list. I want to say that it's either 150 or 400, but neither of them are good. Vulnerabilities per day in the Linux kernel in some cases. Um, and I think that's a testament to how dangerous the kernel space is when we talk about security. It really is. In my opinion, Linux should sort of be treated as single tenant in a lot of ways because of that. These vulnerabilities come out. Not every vulnerability is going to impact the exact same security, but there are a ton of things that can go wrong. And we're not picking on any projects here because this is an inherent problem with Linux and particularly Unix itself. And this is something that we have to, as an industry, understand in order to build truly secure software. There's a few ones that just happened relatively recently: copy fail, dirty frag, fragnesia. These are really interesting ones because they were very dangerous. They were kind of, I think a lot of friends of mine were sort of joking a lot about how insane they were and how it's just like one just keeps coming out every day. These are particularly dangerous, and I think these things are going to become more common. And do keep in mind, like all software, it's a moving target. Um, I really encourage you to look at the diffs between kernel releases, not necessarily the code, because I think it's too much of it, but the line diffs. How many lines changed? They're pretty large. And I think that's a really important thing for us to understand is the kernel is always going to be a moving target. New vulnerabilities will be introduced. We have a lot of good tools these days. There's lots of advanced models looking at this stuff, but it doesn't improve the security. It improves the security in the short term, but I'm not sure that it will always be able to catch everything. You can see this uh, in the types of vulnerabilities that we were thinking about 10 years ago versus now. Actually, interestingly enough, like I think the CPU vulnerability space is a good thing to look at in this regard because There's new vulnerabilities that come out that are kind of variants of things that have already existed as well. Uh, it's it seems likely that variants of existing bugs, as you can see through this, they're fairly related, um, is going to become more commonplace. Uh, so as I was saying, there will be a lot more of these, and I'm very confident in that. There's probably a ton of them that are in um, uh, disclosure process right now that I'll be able to point to as soon as that's over, and it'll just be um, a bigger list next time. So what do we do about this? Because I've given you kind of a doom and gloom picture of Linux kernel of the Linux kernel, and I love Linux. It's not about making it seem like it's not a good thing to use. It's very important, but I think we need to accept the risk that we have gotten ourselves into with using the Linux kernel. Uh, and so that's where the microVM idea comes in. MicroVMs are about giving each workload its own kernel. If the kernel isn't secure enough for multi-tenancy, then we have to have a layer of the system that is secure for multi-tenancy. And this is about enforcing that with hardware as well. Hardware is very capable, and I'll probably rant about this a little bit later, but we as software developers are not very imaginative. And I think part of that is because we're kind of hired to solve problems, right? Not to necessarily create cool stuff. And I think we, though, underestimate how bad the foundations we are built on are. But I think also people underestimate how flexible hardware is. While it's true that hardware was not developed in a vacuum, CPUs often have features that directly correlate the kernel features and stuff like that. Um, there's still a lot of things that are possible that not a lot of people think about. Thinking of Edera's kind of concept of a separation kernel and stuff like that, where there's different paradigms that people haven't put into practice as often that I really encourage people to think about when we do this. And uh, we need to assume malicious intent. Uh, and this is proven through the new vulnerability or the new report that just came out. Because I think uh, there's a tendency for us to assume that if there's a human to blame, that some risk is mitigated. But now we're in the age where agents are just doing things, right? And non-determinism is becoming more important than ever. Um, so we have to assume that things can go wrong and that every application is potentially untrusted in our security model. I think that's truly the only way we're going to solve this problem. And microVMs are all about this. And it's also about isolating everything so that kernel compromise doesn't affect other applications. So that's effectively making sure that a kernel compromise and one workload does not impact other workloads. And the goal of that is to contain things, to truly contain the problem. And I think that's super important. And this type of architecture would have likely prevented the issues that we were discussing earlier. And we need to build in trust boundaries. So this is all about making sure that you actually architect your systems with a high degree of trust. And importantly, microVMs are really trying to give you this idea of don't change anything about your application. Now, to be clear, not every microVM situation out there is like this, but the ones that you should be using are. I think we have to be able to run applications as they are because as system developers and as infrastructure owners, we cannot really be pushing this on developers when this is truly a problem of how we've architected our application platforms. Um, and importantly, with microVMs, the blast radius is shrinking from the node to the workload. So if something goes wrong inside of a workload, it can only impact that workload itself, the actual physical instance of that workload. And I think that's very critical. Um, so what does this solution look like? Um, in this example, we're showing Edera, but we have a type 1 hypervisor that is deployed on either your cloud instance or bare metal. And once that's deployed, we give you a concept called zones. And zones are a combination of a virtual machine, Linux kernel, and a management layer. And it allows you to launch independent workloads inside of those zones and create them very cheaply. And the idea is that a single kernel bug, which we're still running Linux here, just in isolated zones, can only impact one zone. And that lateral movement then becomes next to impossible. Our hypervisor is very thin. It has a small attack surface, very well auditable, and the vast majority of the control plane is written in Rust, and that's very important for us because we believe in as much memory safety as we can possibly get on today's systems. And importantly, this is all backed by the hardware enforced boundary. We're using the features of the CPU in order to do this. But importantly, even if you don't have virtualization extensions or nested virtualization, we also function in those systems as well through a very advanced hypervisor technology that is all about pair virtualizing even the CPU itself, while still running very performantly. And I think that's a very important point of this is performance is very key to a lot of the systems. You can't make that security performance trade-off truly. So in the context of the Hugging Face OpenAI stuff we were discussing earlier, um, without Edera, you get entire cluster node access, credentials stolen. It's a bad day. It's the reports that we're seeing here. But with Edera, if you get code execution inside of a worker, you can't really escape the zone itself. So the cluster is protected, and we do a lot of um, uh, things in Edera's technology to make this possible. But importantly, it's also easy to adopt, which is again very critical for people that are deploying this. So what does a shared kernel versus a microVM look like? The shared kernel, you have one Linux kernel and many tenants. You have a namespace boundary. You exploit one namespace or at one tenant, you reach all tenants. These are very fast and they can get high density, but it comes at a severe trade-off. Again, from a technical perspective, this is quite literally just replacing some structure values in the Linux kernel. It's not anything more than that. And some additional access checks, of course. Um, and then with a microVM, you have a kernel per tenant. Your hypervisor is acting as the boundary. It's effectively enforcing separation between everything. You exploit one thing, you reach one thing. It's very fast. It's fast enough within a few percentage points of performance. And the density is very sufficient for the vast majority of use cases. I think we have a tendency to focus on fast numbers and that look cool but in reality, the number that matters is it better or worse than what you already have? And in many cases, microVMs can actually be faster because of the way they're architected. So what does the microVM landscape look like? We have Firecracker, which is all about serverless and function as a service. It's really when you use this, mostly when you want to run a whole bunch of things with fast cold starts. I tend to think that it comes with a few trade-offs because of feature sets and things like that. I think a lot of people also end up having to modify Firecracker to get it to work for them. Cloud Hypervisor is about general virtual machines, has a modern device model, VirtIO, stuff like that, but not using QEMU and those kinds of things. Kata containers is focused on drop-in OCI, so it's really focused on just the containers use case. it uses multiple different backends, but one of them is Firecracker and Cloud Hypervisor as well. They also have their own, I guess, like alpha beta thing called, I believe it's Dragon Ball. And then Edera is really focused on the multi-tenant case and GPU use case, but also on virtual machines and providing kind of a single layer to run your infrastructure in a more secure way, no matter where you're running things. So we are fully para-virtualized. We can run in places like AWS without nested virtualization. We have near native performance and we're commercial, but we have a lot of open source components. Um, and importantly, all of these will give you a per workload kernel. So if you're running one workload as at the concept or the layer that it gives you, Firecracker being a VM and Cloud Hypervisor being a VM, Kata containers being a container, Edera being a zone, then you are getting one workload to one kernel. And that's very critical part of the security model and what enables all of this. So I have these little slides in here to be able to rant a little bit because I am very intimately involved in the software and stack and I have a vested interest in this stuff. And also, I was a user at one point of a lot of these tools. Uh, and I think importantly, we need to think about how we architect our applications better to support isolation. Um, it's interestingly enough, the uh, the movement towards containers has really uh, created this explosion of, I would say, microservices, right? And I think that's enabled us to get a little bit better isolation and fault tolerance and things like that. But that model fits very cleanly on top of a lot of what I've just talked about. Uh, and I think we need to stop being afraid of that a little bit and accept that like there are real ways that we can actually use these technologies today. Which leads me to my next thing, which is about the systems developer side of it. Um, and this is really where the real rant is, but we need to build better systems that users can actually use. I think I personally am very frustrated with the kind of lower level programming initiatives in the world because there a lot of it seems very cool and there's a lot of cool stuff and there's a lot of good research and there's a lot of people with really interesting research papers on this stuff, but we have to put it into practice. We actually have to like change the infrastructure and the tools that we're giving people. And um, I also think that we can't just wrap something and call it a day, right? Like if you're building a wrapper of Firecracker, that's that's not going to give you the most secure system. We need to accept that we have to change different layers of the system in order to fundamentally rethink about how we're architecting our systems. Um, when the age of AI, I'm more scared than ever, like legitimately scared of the architecture and the security of systems today, because ultimately a hack of a bank is going to impact my life and everyone's lives. And we have this infrastructure in the world for a reason. It suits a purpose, and we need to create the tools today that will enable those people who are building those systems to keep their users more secure and prevent data leaks and also exploits. And that means getting a little bit uncomfortable, maybe going away from some of the things that we're used to, uh, maybe being a little bit radical in our architecture decisions. But I think really what matters to me is that we're looking at what we've done before and looking at the places we can improve. And I think Linux is an example of a place where that's very critical because there's a lot of things that we've done over the years. And although I'm afraid of creating second system syndrome and things like that, we do need to do better. And ultimately, um, that this is a ask for systems developers to fight in the mission to get better tools to people so that these problems are easier for developers to solve. So when we talk about microVMs, there's honest trade-offs that I think are very important for me to disclose. Cold starts are often higher. Um, to be honest, people will quote all sorts of numbers to you. You'll read a research paper and it'll say 10 milliseconds. The vast majority of that isn't really relevant to the average user because the reality is that things change. There's certain use cases where cold starts being really small are good, like functions as a service and stuff like that. But the vast majority of time, I mean, the microVM startup time isn't even in the largest part of the time it takes to start a container on Kubernetes, for example. Memory overhead is often going to be a risk, and there's lots of ways you can mitigate it, like we have copy on write forking in Edera and things like that. But memory overhead is going to be a bit of a thing because when you have each kernel has some amount of overhead in memory, and then which is just the risk of attaching a kernel to every workload. Some systems require nested virtualization, which in some systems and clouds is either not possible or hard to attain, or requires maybe moving instance types you're familiar with. And GPUs and device pass-through is an evolving story, and there's a lot of problems with vendors and things that it gets very complicated. But ultimately, those are pieces of hardware that need to connect, and we can't undervalue how important that is in these systems. But what you get in return is a very secure boundary for your threat model, and you can actually rely upon it. A few non-obvious things that I'll run through real quick. eBPF often doesn't work. We have integrations with Falco and Edera, for example. This is one of those things where I feel like the vast majority of people who want to try to solve this run into this and then feel like they're helpless. And so this is a very important part of solving this space. Um, and to be honest, we built a lot of tools that rely on the lack of security. I can't tell you the number of Kubernetes tools that have issues where they run in host namespaces or lots of scripts or even homegrown stuff that runs like that. Um, with Edera, we have this concept of a root zone. So you can either run Kubernetes inside your root zone, which is also protected by the hypervisor, or you can run it in a separate zone itself. That gives you a much higher degree of security. And resource management comes a little bit harder because suddenly the math is a little bit different. You have to think about that. VMMs will always have a little bit of overhead. Um, and good ones will focus on reducing that. And I think that's an important part of that. And we've been very focused on low overhead interfaces and scheduling to compensate. In many cases, we're often faster in some regards because of the intense focus on that. And I think microVMs have to kind of contend with those problems. So the blast radius, all this is trying to show is that the blast radius is contained into a zone instead of the entire system. So one kernel compromise or one tenant compromise does not explode into significant risk across the system. So the takeaways are there are production-ready microVM platforms today. Containers aren't a security boundary. The Linux kernel won't save you. Adding another namespace to the Linux kernel won't save you, and you should probably know how your containers run because it's very critical for how we use systems today. And then if you want to get started with Edera, you can sign up for Edera On, our free one-node access program. You can drop Edera into an existing cluster in under an hour at on.edera.dev. Questions? I hear there are questions. Uh, how can I see the questions here? Uh, Can someone send me the questions, please? Thank you. Uh, if micro-VMs are becoming the isolation primitive for secure multi-tenant AI, where do you see confidential VMs fitting into the architecture? Are they complementary technologies solving different trust problems, or do you expect confidential computing to eventually become a requirement for micro-VMs? This is an interesting question. I think confidential VMs are very interesting tech. It's very advanced, and often I think most confidential VMs discussions probably end with this is too complicated. And that kind of goes to my systems engineer kind of rant a little bit, is that we have to make these things approachable. Um, Confidential computing is very interesting though. And I think it will only succeed if it can be done so transparently you don't even know that it happened. And what we've been doing with Edera is really focusing on this idea of providing all the things that people need in order to feel confident in their infrastructure. I see that confidential computing in general, as it starts to progress, will become integrated into existing tools more and more often, as opposed to a kind of niche thing. Um, I don't believe it will ever become a requirement. And my reason for that is very simple. Um, the way it's architected today, at least, it doesn't make it approachable. It makes people think about it too much until it's literally just a checkbox. And to be clear, I'm sure you can get some checkboxes on some cloud providers today, but it's not the same, I think, as the multi-tenant side of things. Um, that is what's really required. Uh, yes, the biggest trade-off of Edera is, uh, to be honest, the most times that I see friction are usually when people are doing something insecure and they need an exception because of whatever reason, right? So some of these examples are people running with host networking, or uh, people who want to institute Edera across their entire system but run into the problem of certain users needing, uh, host access. We have a lot of work that we've done in order to make this still approachable. So, for example, you can access privileged mode and effectively unleash containers and turn off all the security primitives while still running in Adera. So in Adera, you can run kind of, skipping permissions on your AI agent or whatever, while still trusting that it can't affect the host. But most often, friction comes around when people are doing something insecure and it requires organizational change. And I would say the second thing is always going to be performance. Um, we work very hard on performance. We have done a ton of work, and we're a few percentage points off from the host system. And there are some cases as well where we do a little bit better, and than the host system, just due to the algorithms and stuff we use. But uh, that's always going to be a thing that we have to think about, because performance differs between people, right? How one person sees performance is different from how another sees performance. It's almost like throughput versus latency, right? You can maybe do better throughput, but at the cost of latency. But if you want to lower latency, you have to sacrifice a little bit of throughput, things like that. And we try to give you same defaults. But that is often a thing that people will question or ask about. Um, Vast majority of people are testing performance on Adera for that reason. And we unlock new performance things that we didn't even think were possible on a daily basis. Uh, Anything else here? Awesome. I think that's it then. Thanks, everyone. I greatly appreciate it. And hope this was enjoyable and interesting. And definitely reach out if you have any questions. And I'm gonna go back here and say definitely try Edera on. It's a very fun and interesting thing. Awesome. Thanks, everyone.